Travis Collins holds MS and PhD degrees in electrical and computer engineering from Worcester Polytechnic Institute in Worcester, Massachusetts. Dr. Collins' research is focused on small cell interference modeling, phased array localization, and high-performance computing for software-defined radio. He has extensive experience developing for SDR applications in many different software environments and hardware architectures, and remains active in several open-source-based SDR projects. Currently, Dr. Collins works as a development engineer for analog devices in the Systems Development Group. There, Dr. Collins is responsible for transceiver applications, among others, and works heavily on hardware and software integration projects.
Good morning, good afternoon, good evening to all those watching live and to those watching on YouTube after the conference. My name is Travis Collins, and my talk is entitled GNU Radio in a Direct RF World. In this talk, we'll focus around using very high-speed converters in GNU Radio and how I use them personally with these very, very fast devices. When we're talking about fast, we mean multiple gigasamples a second, so very, very high-speed devices. Now, just a little background on me. I'm a senior algorithms engineer in the systems development group at Analog Devices. I work on a number of different products. I help maintain GRIO, which is the auto tree module to connect to a number of devices that ADI produces. I work on a number of libraries like libio, lib809361, a few others. I maintain the Python module PyADI-IO. I hope everyone's sensing a theme here in regards to IO. And I do support a number of different hardware components like Pluto, the FM comms boards, other transceivers, other high-speed components, sensors, low-level things. And if you've come to the ADI support forum called Engineer Zone, it's likely that I've answered your question about Pluto or GNU Radio or something similar. Now, just a bit of outline of the talk. First, I just want to have a little bit of background on architectures of different radios, just so everyone's on the same page when I talk about direct RF. Then I'll introduce a modern direct RF solution that I work on a daily basis, just to bring some context and show some cool pictures of hardware, like everyone likes to see. And then we'll move on into the data paths and talk about how fast these devices really are and the amount of data that's coming off of them. And then we'll move on into a discussion of some strategies that I've used or I recommend, or different tools to help handle that high-speed data coming back. So let's just begin with some background. Historically, there are three main radio architectures: superhead, zero-IF, sometimes called heterodyne, and the latest, which we're really interested in, called direct RF or direct sampling. Now, superhead are devices that have a single or multiple IF or intermediate frequency stages. These devices are really considered like traditional designs, but modern SDRs, modern radios that people develop still use this architecture. Here on the left, we see just an image of an X310 that has a pair of twin RXs, which are actually superhead designs, as well as like a super old school kind of radio that you would see probably in your grandfather's basement or something. So superhead, the big advantage is that the analog performance is pretty extreme, just because we can put filters and all kinds of processing or analog components in the signal chain, but at the cost of board space, power, number of components, and usually flexibility. So when you put a filter down, usually it's pretty fixed. Now, moving on to zero-IF, which is usually what we think of when we talk about SDRs or modern SDRs. This architecture uses no IF stage, so instead it uses just a single mixer to mix things down to baseband. This architecture is in devices like Pluto, like Blade RFs, Sidekicks, USRPs like the B210. The new N series devices have devices like these, like anything that's based off of the 9361 or 71 or any transceivers from ADI all use this zero-IF architecture. Zero-IF is the big advantage is like it's highly integrated, so you don't need a lot of components around, and it's very flexible, so you can have large LO ranges, large bandwidth changes. But the consequences are that you need algorithms to handle things like mixing products or desync components that are involved. And this is why 0F has only been around for a couple of decades compared to superhead. Now, finally, this brings us to the last architecture, direct RF, where we basically hook a very high-speed ADC or DAC directly up to the antenna. Here we're kind of showing the converter hooked up to an LNA, which you would naturally have, or a PA on the DAC side, but a very, very simple receive or transmit chain. Here we're just showing a simple FMC-based card, and these are really common in the space. And these would just hook up to like a standard FPGA or a bigger chassis with multiple of these cards in it, but very, very high-speed converters inside these on the gigasample per second realm. Now, but the real question is why direct RF? What is the really kind of design advantage here? So it's not all good. There is some bad. The main advantage is that we can decrease the complexity of the RX and TX channels. So we can remove components, we can remove mixers and lots of filters and other additional pieces, and really simplify that chain. We can reduce the number of independent channels that you might need if you need to pull in a lot of bandwidth. So instead of having like 4 receivers that all have a specific bandwidth, you could have a single receiver or a single ADC that pulls in that entire bandwidth slot. And as I kind of mentioned before, smaller footprint because you're less devices in the chain. And the device, since you got less components, it'd be much, much simpler to synchronize multiple of them together. Now, the bad side is that you have to be able to handle that kind of data rate. So when you have gigasamples a second coming in, that's a lot of processing power that you need on the back end to handle. And I would say like the less commonly known downside to direct RF is the dynamic range requirements. So when you're pulling in gigahertz of bandwidth, so we have just a little kind of plot here over frequency range. If you have a signal that's very loud, which we have on the right here, that's going to drown out possibly other signals that we'd want to be interested in, like the one on the left here. We might want to, this is the signal that we're interested in, and we can't simply turn up the analog gain because we would actually saturate because this signal would dominate the other ones. So it's a very common problem in direct RF is this dynamic range problem. Now, just to bring some more context, let's look at an example device that's used in this space, something that I use on a daily basis. Something like the 809081 or 9082. So these are highly integrated chips. So on a single chip, we have quad DACs, quad ADCs that have very high bandwidths. They can be on the order of 4 gigasamples or 6 gigasamples on the ADC side and 12 gigasamples a second on the DAC side. And then these chips have lots and lots of DSP inside them. So for example, grab my pointer here again. In the red, we have the TX or the DAC side. We have these fine up converters and coarse up converters. And then on the ADC side, we have the reverse. And we'll get into these what we call channelizers later on and how you can use them for different applications. Now, just to give you some perspective on what these devices might look like, if you get them in your lab or you're just interested, here we just have a 9081 eval card. So this is what you get from ADI that's slotted up to a ZCU 102 Xilinx eval kit. And for reference, here's just a Pluto that we say. So these kits these boards are pretty large. The chips themselves are pretty big on them, but super highly integrated. On the right here, we see that all 4 ADCs and all 4 DACs are pinned out, and we have a big power solution, just to give you some reference on what this device might look like. So next, I want to discuss a bit more about the speed or how fast these devices really are. And to do this, I think the best perspective is actually from the HDL workflows, where we actually can see the data coming in from the converters. And how fast the clocks are in the places where, inside the FPGA where we think everything is pretty fast in general. But I wanted to start from just give you perspective on something that's a little bit more familiar. And we're going to start with the actual Pluto reference design or the reference design that's used for 89361 type devices from Analog Devices. So in this image, in the middle, we actually see like an FPGA carrier board In the center of that is the fabric. So these are like the blocks inside the programmable fabric itself. On the top, we have a representation of the zinc or microblaze that we're running on the carrier board. And this will be connected through DDR into the fabric. And then on the right, we would have a FMC card like an FMCOMS, or in the case of Pluto, this would just be directly connected instead of through FMC up to the fabric of the FPGA. Now, in the case of 9361, data comes in across LVDS or CMOS at about 122.88 megabits per second, or megasamples a second, excuse me. And then that data is rearranged because it doesn't actually come in at 12 bits per clock as you might expect. It's a little bit different than that. So we actually reorganize that, and outside of this interface core here, we actually get samples that you would expect. So here we have 32-bit wide samples. So these are for dual channel I plus Q. And then those are packed into a bigger sample and then passed into DDR. So in this configuration, you have a data rate at about 61.44 megahertz at most. And this is actually per valid, based on the valid clock or the valid strobe that you get from the transceiver. So in LVDS mode, the main clock inside the system will actually run at 4x the data rate. So this will be up at technically around 250, but you'll only get a sample every 4 clock cycles. In CMOS mode, like how Pluto is configured, you get 1 sample per clock cycle. Now, if we transition over to the 9081, things are a bit different. You can see first of all that there's a lot more IP cores inside the FPGA. But one of the main differences, if we start off at the FMC card, is that the interface is much, much faster. So this is actually using GESD, GESD 204B or C, depending on the mode that you're using. And that's a JEDEC standard where we can generate a high-speed link to the device instead of having many, many LVDS lanes. So data comes in at this high-speed link, and then we repack it in a number of different steps through our different cores. And then at the end, we can see that we have a data width of 512 bits at 250 megahertz. So that translates roughly into, or exactly into 16 samples per clock, which will actually generate 4 gigasamples per second. So pretty extreme. We're talking about a change in roughly 16 times 2 or 4 rates difference between the 9361 or the typical transceivers you would see in something like Pluto and a device like this. So pretty extreme speeds. But obviously, people would want to use these in multiples. So we have designs like this where we're taking 4 9081s and putting them on a single board. You can think that in a single config or a single device where we're getting 4 gigasamples a second, something like this would produce 4 times that. So pretty extreme amounts of data. So for reference, just to show you what this might look like, back to our old kind of unit of measure here, Pluto. So this is a pretty beastly board with 16 transmit and 16 receive channels, all synchronized together on this guy. And then we had to see it all running and lit up. Here's just an example of it running with a VCU 118. This is just a standard Xilinx eval card or eval board. And we can see all 16 transmitters and receivers all pinned out on their MMCX interfaces here. And so the LEDs are kind of bright on this rev, but they've actually been calmed down quite a bit. But just to show you some kind of cool hardware here. Now, but the question is, how do you use gigahertz of bandwidth, right? Are you just directly connecting this into GNU Radio? Maybe we can ask a simpler question. say we're talking about USB or Ethernet or PCIe, how close can we get to a typical throughput using those type of interfaces if we wanted to stream from that the ZCU102 or the VCU118 back into GNU Radio. So if we just take like the theoretical max of these interfaces, this is ignoring overhead or any encoding or jumbo frames or those types of things, we don't really get close. So PCIe and 10 gig are kind of the realms that we want to be in. But we're talking about PCIe that we would have almost one lane per sample. That's the kind of order that we're talking about to actually just move data from the eval board to back to your PC for GNU Radio to process. So pretty extreme speeds here. Now, when we're actually talking about handling this data, if we can get it back to the device, of course, or get it back to our PC, of course, there are four main approaches that I've taken or that I've recommended people use when they're trying to use a device like this with GNU Radio. The first thing is really always, when we're talking about dropping samples on the floor, we usually refer to that as overflows. And you'll see these O's and U's that appear. So these kind of are part of the Pluto SDR blocks and all of the FM comms blocks. But we've kind of grabbed this this O and U notation from the USRPs, if you're very familiar with overflows, underflows in those blocks. Now, in your application, do these matter? Do you care about losing data or pulling a buffer and having the next buffer not be contiguous to that? So that's really dependent on the application that you're going after. Another option is can you work in bursts? If you get a big swath of RAM of data that's contiguous, does that meet your needs? Successive chunks of memory might not be contiguous, but where your gaps are. Can you create a flow graph to handle that? And then the other three, or the three other approaches, really kind of focus on knocking down the data. So pulling out the signal of interest that we care about before passing things into GNU Radio. But let's talk a little bit about how you might approach dealing with bursts or collecting large swaths of data. And we'll do this from the perspective of GRIO. So if you look at the block masks of a block like Pluto SDR source or FMCOM source or the generic IAO source blocks, you'll see this parameter called buffer size. Now, what this actually does is that it defines how big buffers in the hardware will be. So when I'm talking about hardware, I'm talking about actually Pluto itself. So how much space in DDR is it allocating for samples? And the distinction here is that this buffer will be contiguous. So any data that's saved in it for a single buffer will be contiguous guaranteed. Successive buffers do not have that guarantee. Now, back in GNU Radio, what we actually do is that we emit a tag so that when we get a fresh buffer, we tell everyone downstream that, hey, this is the start of a new buffer. Data before it might be discontiguous. And depending on how you build your flow graph, it may be possible for you to handle considerations where buffers or large, I would say if you're talking about GR buffers, several GR buffers might be contiguous, but then you might have a break. But you could easily identify that with these tags. So one thing to note is that these buffers can actually be pretty large, these hardware buffers. So Pluto has 512 megabytes of RAM on board. So you technically can increase the default buffer, which is 2 to the 23 samples, and make that much larger. And what that effect would have is you could do a capture, which was very long, multiple seconds at full speed, and then pipe that back into GNU Radio, and you would have lots and lots of what I might call GR buffers which the scheduler will handle that you could operate on in continuity. Now, if you bump up to something like the VCU 128, which we support for that quad board and the single card that I showed previously, that has 8 gig of HBM on board, so that's a super high speed memory interconnect. Now, 8 gigs isn't a lot when you're talking about multiple 4 gigasample converters. But if you needed to do a capture, that would get you a serious amount of time, relatively. Now, the next step might actually be trying to offload some of the processing into the FPGA itself. So there are great frameworks out there like RFNOC, but sometimes when we're talking about doing processing in the FPGA, there are limits that you'll run into when you're doing this processing. So one of the common constraints is what we call Fmax rates. So Fmax is the maximum frequency or maximum clock you can run in FPGA, and this will be related to some logic, some DSP or some block RAM. And this will be really the upper limit of how fast you can run things. And this is generally a lot smaller than the achievable data rates by the converters that we're talking about here. Therefore, you need to transition things where you're processing multiple samples at a time if you really want at that rate. Or you can channelize inside the FPGA, add decimation to knock down the data rate. And if you are looking at working in this area, developing IP in this area, 2 resources that I would highly recommend are if you look at the vectorized block library that's inside HDL Coder, or the SSR or super sample rate blocks inside System Generator by Xilinx. So these blocks are designed to work with multiple samples at a time. They're like filters or FFTs and things like that will work at gigasample rates. So if you want to run things at rate, there are options for you out there that exist in these tools. And they're all Simulink based, so they're actually pretty straightforward to use. Now, another option is actually to use some of the on-chip features that exist in parts. Say we have an application where we're looking at a signal in the spectrum here. This is a lot of bandwidth. This is, say, 6 gigahertz of bandwidth. But there really only are 2 signals or 2 bands that we care about here. And say, these are the things that we want to pull back into our device. Now, one thing we actually could do is we could say, hey, why don't I take this guy, shift him downward a little bit, and then I only need to pick out, this swath of bandwidth. And here's kind of an example of that, where we have some signal here, this multi-carrier GSM that we're pulling in at 245, and then we use a NCO and downshift it to the center of our band. And then we only have to return data at 122 megasamples a second. So you can move around the data that you care about and then return the data that's useful to you back to the device. And this is where we get into those channelizers that we kind of talked about before. So inside the 9081 and 9082, there are a coarse and fine DDCs where we have NCOs that we can all independently shift. So we can move those signals around in frequency and then decimate. So we can kind of, pull the different parts of the spectrum that we care about in and really reduce our data rate and, knock things down to something that's more acceptable in the FPGA or in GNU Radio itself. So the final approach that I usually take is actually in regards to, say, like an application itself. So say we wanted to build a 802.11 beacon receiver. So beacons in 802.11a actually are relatively infrequent. So here's kind of a beacon here, a beacon here, a beacon here. They occur roughly every 100 milliseconds, depending on configuration. However, to actually figure out where they are, you have to be continuously receiving because the network is random. And on the bottom here, we actually have a flow graph from GR802.11 where we're splitting out frame detection and then processing. So once we actually detect the frame, we can process it. And one technique we can use is that we could actually put most of this kind of detection or synchronization math that we have to do, stuff that kind of has to always be running, throw that into the FPGA. And then once we know where the start of our frame is, we can kind of cut that out and then pass it back to GR on the host. And by doing this, if we're in the case of a beacon receiver where we only care about beacon packets, we can actually reduce the data rate that we're pushing back by 250x. So that's an extreme reduction in data rate that we see, and that could in GR doing, say, this at 20 megahertz or 20 megasamples a second would be complicated or challenging. But say reduce that by 250, that's pretty reasonable. You might be able to actually pull it off on like a Raspberry Pi or something. Now, just to kind of close things up here, DirectRF devices are coming. They're becoming more and more common. They're coming with actually fixed logic inside them that you can take advantage of to knock things down to get the data back that you care about. But as a user, you need to understand where bottlenecks might exist in your system. Like, if you want to do certain things in the FPGA, what's the clocking limitations that you have there? You might have memory limits on how fast you can actually write to DDR. The link that you're using might actually not be capable, no matter if you're using 10 gig. And where do you want to do processing in your system? So really, the mental model of real-time and GRR and GNU Radio needs to shift a bit. That doesn't mean you can't use it. It just you need to have certain expectations. And actually, what I say is look at the data that you care about in GR and use the hardware, use the features of the hardware that exist. Now, so that's the conclusion of my talk. I want to thank everyone on the line. So if you want to reach out to me, my username on GitHub is tfcollins, and here's my email. Thank you.